With this, we are now at the end of this 20 hours course titled as Multiphase Microfluidics. I have listed here the topics that we have discussed. We started with the introduction to microfluidics. What are the physical effects, or what is different, or what can be different in microchannels, as well as the basics of microfluidics and multiphase flows. So, in microfluidics, because the interfaces are generally large and capillary effects are important, so more than one need to understand the interfaces, capillary effects to understand the microfluidic, the multiphase flow behavior in microchannels. The second part of this, the interfaces and capillary effects, we have divided into two different sections which were discussed at two different times during the course, or at two different stages during the course. The first stage, where we talked about the surface tension and gas liquid or liquid liquid interactions, we discussed at the start of the course. Once we have developed a bit of understanding, in the next stage we discussed the three phase contact angles, where we also looked at the droplets sitting over a sphere and the contact angles and things like that. So, once we have understood the basics of multiphase flows, or the fundamentals, the definitions, the equations, Young-Laplace law, Casey-Baxter law, and the terms that we use in this area, then we looked at the flow regimes that can happen in gas liquid flow and liquid liquid flows. And it turned out that one of the most often and most important flow regime in terms of the applications is the Taylor flow regime. So, we have devoted a large chunk of this course to the hydrodynamics, heat and mass transfer in the Taylor flow regime. We also looked at that when because one need to precisely control the size of the bubbles and droplets that are being generated. So, we have looked at in a brief lecture, we have looked at the bubble and droplet generation that are and the mechanism of it, and the equations, the mechanism of bubble generation at a T junction in a flow focusing device has been discussed in this. While dealing with the gas liquid flows, void fraction is a very important information, and designing any microfluidic device, one need to have an idea of the pressure drop, because that will determine the energy that is required for the pumping in the fluid. So, we have in a lecture we have also discussed the void fraction and pressure drop in gas liquid flows in microchannels. We have briefly touched upon the annular flow and looked at the analytical solution for an ideal annular flow, and how we can calculate the interfacial radius or the thickness of the liquid film and the pressure drop in ideal conditions in annular flow. However, the conditions are not always ideal, or almost never ideal, especially when we are dealing with gas liquid flows, and there will be instabilities at the interface. So, one need to look at further the hydrodynamics of slug annular and annular flow, and this is an area which has not been explored fully in gas liquid flow in microchannels. Then we have also looked at flow boiling in microchannels. So, the evaporation and the nucleate boiling and the questions that are there to address that which boiling it is it the nucleate boiling or the evaporative boiling which is dominant, is still not addressed, and one need to further investigate to establish the dominant mechanism of flow boiling in microchannels. Taking a diversion from the entire theme of this course, we have also looked at the inertial microfluidics, where the main discussion was about inertial focusing, the focusing of the particles in a channel, and we looked at the rigid particle focusing, but one can also look at the focusing of the flexible particles, cells, bubbles and droplets in the channels, and it has, as we have seen, that it has a number of applications in microfluidics. Then during the middle of the course, we have introduced the computational techniques for modeling multi-phase flows, and because the interface size is large in multi-phase microfluidics, so one often prefers to capture the interface. So the interface capturing techniques such as volume of fluid method or level set method or phase field method or lattice Boltzmann method are more popular in microfluidic applications rather than say Euler method, where the interface cannot be captured, and one need to rely on the closing or the closure equations for the momentum exchange between the two fluids, or the gas and solid or gas and liquid phases. Then we have briefly discussed the different flow measurement techniques, and in one lecture we also looked at the basics and fundamentals of microparticle image velocimetry, which can be used to understand the velocity field, and with laser induced fluorescence the temperature and concentration field in microchannels. And in the last two lectures we have looked at the number of applications and the potential of the microfluidics to impact the different sectors and our day-to-day life. So I hope that you have learned some of the basics, and this course has motivated you to learn more about microfluidics. We welcome the suggestions to further improve the course. I would also request you to post any questions or doubts that you might have, or any suggestions that might have that you might have about the course, to post on the course website. Thank you and good luck.